Hi, welcome back to recitation. We've been talking about Taylor series for a number of functions and rules by which you can compute Taylor series. I have here an example that I don't think we did in lecture. So this is the function f of x equals secant of x. Now, unlike some of the other ones you've seen, there's not a really simple formula for the whole Taylor series of secant x. So what I'd like you to do is not to find a formula for the general term, but rather just to use some of the tools that we've learned to compute the first few terms of the Taylor series for f of x equals secant x, say up through the x to the fourth term if you wanted, or even a little further if you were feeling ambitious. So why don't you pause the video, have a go at that, come back, and we can do it together. So welcome back. I asked you to compute the first few terms of a Taylor series. One thing you can always do in this case is you can go and you can apply the general formula that we have for Taylor series and use it to compute the series that way. So in order to do that, you just need to compute a few derivatives of your function. So remember that the general formula for a Taylor series is the Taylor series for f of x is equal to the sum from n equals 0 to infinity of the nth derivative of f taken at 0 divided by n factorial times x to the n. And since we're only interested in the first few terms, this is f of 0 plus f prime of 0 x plus f double prime of 0 over 2x squared plus dot, dot, dot. All right, I'm not going to write out the next few terms. And if you wanted to apply this formula to secant of x, what you would have to do is you would have to compute these derivatives. And so we could try doing that. So in our case, f of x is equal to secant of x. So f of 0 is secant of 0, which is just 1. So then we need to know f prime of x. So that's the derivative of secant of x. So this is one you should remember. This is equal to secant x times tan x. And when you plug in x equal to 0, well, the tan x is 0. So f prime of 0 is equal to 0. And then you could keep going. So you could compute f double prime of x. So we would have to compute the derivative of secant x tan x. And you would do that by the product rule. You know, you take the derivative of secant of x, and that gives you secant x tan x times tan x plus, and then so you leave secant of x, and you multiply it by the derivative of tangent, which is secant squared x. And now when you put in 0 here, you get f double prime of 0. Well, OK, so this has a tan x in it, so that part's going to give you 0. And here we end up with secant of 0 times secant squared of 0. So that's 1 times 1 times 1. So that's just 1. So f double prime of 0 is 1. And you could keep doing this. Now, one thing you'll notice is that this is getting more and more complicated. I mean, we can simplify this expression a little bit. We could write it as secant x tan squared x plus secant cubed x. And there are all sorts of trig manipulations you could do if you wanted to try and rewrite that in some simpler form. But fundamentally, it's more complicated than the first derivative was, and that's more complicated than the function, and it'll keep getting more complicated as you compute more derivatives. So we can do this. So far, this shows us, by the way, that this is equal to 1 plus 0x plus x squared over 2 plus dot, dot, dot. And if you wanted to compute up through the 4th degree term or something like this, that's something that's manageable. But I want to suggest that there are maybe some nicer ways to do it. So one thing to notice is that secant of x is closely related to the function cosine of x. And you know the Taylor series for cosine of x. So one thing you could think to do is to leverage the information that you have about cosine of x in order to use it to get some information about secant of x. So one simple way to do that is that you know that cosine of x is even. It's an even function. Cosine of minus x is equal to cosine of x. So that means secant of x is also even. Secant of x is an even function. And you've seen that even functions, their Taylor series, all the odd powers have coefficient 0. So what that means is without ever computing the third derivative, we can know already that the next term in this Taylor series is going to be 0x cubed over 6. Okay, so that's nice. So the odd terms of the Taylor series for secant of x are 0. Okay, so that's one thing you can get right away. So that gives you, if you like, that gives you half of the terms of the Taylor series. It's a little bit of a joke, but okay. So then you only need to figure out the even terms. That's one way we can leverage the relationship between secant and cosine. The other way is that we can remember that Taylor series multiply just like polynomials do. So if secant is 1 over cosine, that means secant times cosine is equal to 1. Okay? So idea, secant of x times cosine of x is equal to 1. Now, that means that the Taylor series for secant of x times the Taylor series for cosine of x has to simplify just to 1. So we can write down that product as a product of two infinite polynomials, and we can start multiplying term by term. And that'll allow us to solve for a bunch of terms just by solving some simple linear equations. So let me show you what I mean. So we know that, well, let me write it as cosine times secant. So we know that cosine of x is 1 minus x squared over 2 plus x to the 4th over 24, that's 4 factorial, minus x to the 6th over 720, which is 6 factorial, plus dot, dot, dot. And so we know that if we multiply this by the series for secant of x, well, what is the series for secant of x? Well, we've already computed a few terms. We know that it's 1 plus x squared over 2. We computed that already, and we know that the third degree term is 0. So there's some 4th degree coefficient, a for x to the 4th over 4 factorial. And there's some, well, we said it's even, so we know the 5th degree coefficient is 0. So then the 6th degree coefficient we don't know yet. So this is plus a sub 6 times x to the 6th over 6 factorial plus dot, dot, dot. So we know that when we multiply these two things together, it has to give us just 1. All the higher order terms have to cancel because over here we have a 1. So what you can do is you can actually try multiplying these things out. So it's easy to see, for example, that the constant term of this product is just 1 times 1, which is 1, which is good. So that's a check on what we've done so far. And there is no x term because there are no x's. The x squared term here is 1 times x squared over 2 minus x squared over 2 times 1. Well, that gives us 0. So that's good. So this product is equal to, well, it's 1 plus, we saw 0x plus 0x squared. How about the x cubed term? Well, there are no odd terms in this product, so there's no x cubed. How about the x to the 4th term? Well, OK, so how do we get an x to the 4th? We could have an x to the 4th here times a constant. So that's x to the 4th over 24. Or we could have an x squared times an x squared. So in this case, that gives us minus x squared over 2 times x squared over 2, which is minus x to the 4th over 4. Or we could have a constant times an x to the 4th. So this is plus a for x to the 4th over 24. And then we'll have a 6th degree term, and so on. Notice that there's never any involvement from the higher order terms in the 4th power here, right? If you ever took an x to the 6th here, well, then everything you multiply it by has at least an x to the 6th power. So we don't have to worry about that showing up in the x to the 4th term. Well, OK, we know this is actually equal to 1. So we know that this thing has to be 0. This is the x to the 4th term. It has to be 0. So that means that 1 over 24 minus 1 over 4 plus a4 over 24 equals 0. So, OK, so now you can multiply everything through by 24 and rearrange to figure out that a4 is equal to 5, if I've done that correctly. And if you wanted, it would be fairly easy to go back up, and then you look at the x to the 6th term. And from there, you could figure out that a6 was equal to, say, 61 or something like that. I think 61. And you could keep doing this. So this is one way to compute more terms of the series for secant of x. Another thing you could do, which I'll just mention very briefly, I'm not going to show you how to do it, is that you can do a long division on power series. So it actually works out just like this. It's mathematically equivalent. The way you actually do it looks different. It looks like long division. When you do long division with polynomials, you start with the highest order term. Of course, power series don't have highest order terms. What you actually do with a power series is you start with the lowest order term. So to divide this into 1, you'd say, oh, you need a factor of 1, and then you'll have you subtract off 1 times this, and that gives you an x squared plus 2, and so, okay, so you say, I need a plus an x squared plus 2, and so on. So that was too brief for you to understand it properly, but you can go and look up somewhere the method of long division on power series. So just to recap, we talked about 3 methods for computing the coefficients of a power series. There's the formula that you were given, which works and which you could use. In this case, it's a little complicated. Then there's the method of using a relationship between your power series and other known power series. In this case, we can use the relationship that we know our power series satisfies a certain product. We know that our power series times cosine of x equals to 1, and we can use that to solve for some of the coefficients. Or you can also, similarly, when you have that situation, you can also use long division to compute the coefficients. I'll end there.